Hello, my name is Ashley Kipp, and this is my presentation on my capstone on remote sensing methods to locate archaeological sites through vegetation indices on the Florida coast. My partner in this was Dr. Lindsay Cochran, who is the archaeologist at Eastern Tennessee State University, who often works in my site location. So the problem that sparked the idea for this project was actually sea level rise. Because my coastal area is in Florida, this is a big problem. So just in the southeast, with 1 meter of sea level rise, over 13,000 currently documented archaeological sites will be lost. And that's the map you're seeing on the right here. Now that's especially bad in these areas because of relative sea level rise, so the land is actually sinking while the water is rising. So this becomes a big issue because it's happening quicker than archaeologists can take care of, and that's mostly due to a general lack of funding and a lack of archaeologists. To try to address this problem, archaeologists have used existing modeling programs, such as the one you're seeing on the left here is the sea levels affecting marshes model. And that is using vegetation as markers of sea level rise pushing inland to help identify locations where sites might be at risk. There's also specific cultural resource vulnerability studies using a site measuring their distance and elevation specifically from the shoreline, their composition, and their history, as long as issues with development. And these are great methods for mitigating known site locations, but there is a big issue because there's so many things out there that we haven't found yet. So we need a method to be able to quickly find those locations that are at risk of sea level rise. That is not to say that archaeologists have not been using remote sensing methods to try to locate sites. So some of the things that they do use are light detection and ranging, or LiDAR, which uses laser light reflectance to have points come back to get very high definition elevation, which is what you're seeing on the upper right side here, which is actually showing shell rings in an area, and also using aerial imagery, from which they can also use vegetation indices to find crop or soil marks, and you're seeing an example of that in the bottom right. And that is when the composition of archaeology is affecting the soil, and therefore a more homogeneous vegetation like crops, you can actually see lines showing areas that had archaeology. There's also site sensitivity modeling, which uses historical records, things as least cost pass, distance to water, distance to other known sites, to try to find the locations of potential sites. And one of particular interest was in British Columbia, and they used remote sensing and fieldwork and found a connection between coastal forest productivity and past habitation sites, including places that had shell rings that were affecting the tree growth and general productivity, and burned areas, which I'll explain. So a shell ring is a general refuse site or shell midden. When you're living in these coastal areas, you eat a lot of this sort of thing. So you have a lot of waste and you have these big shell deposits. So that's going to add calcium to the soil, while prolonged fire use, campfires, controlled burns throughout the past can alter the soil pH and improved drainage as well, which is what contributes to that tree health and productivity that they were seeing in British Columbia. So the shell rings are going to cause more calcareous soils, meaning high calcium, and the wood ash have also been tied to increased vegetation health, growth rates, basal widths, and infection resistance as well. So all of these things come into account to create my research question, because we can't always look for things in homogeneous sites. So what do you do with a mixed canopy? So can tree health indices and canopy height, on account of the tree productivity and health, derived from LiDAR, accurately locate archaeological sites in the mixed canopy of a coastal forest. So the study location I will be focusing on is the Guantanamo-Matanzas National Estuarine Research Reserve, which I will refer to as GTM from now on. It is in northeastern Florida. It's on the coast in St. Johns and Flagler counties. It is a estuarine reserve, so it has 64,487 acres of wetland and upland habitat. You can see a map of that on the right. Due to the availability of archaeological site locations, my study will be focusing on that northern portion of the reserve. So there is evidence of human habitation in the archaeological record that spans from the Paleo-Native Americans of the late glacial period to the missions and homesteads of the territorial period. So the tool I'll be using to address this question is ArcGIS Pro, and in that I will use 25 orthorectified U.S. Department of Agriculture's National Agricultural Imagery Program multispectral imagery tiles, which I mosaicked from the USGS Earth Explorer portal. And that will be used to create my NDVI. An aerial LiDAR point cloud that has been pre-classified, meaning just that it's already classified the ground levels and differences in vegetations and different returns of those lasers. And that was from the St. Johns County Florida Peninsular LiDAR project, which I downloaded in an LAS zip file that had to be transformed to a LAS dataset for use in ArcGIS Pro. And that was from the NOAA's Digital Coast portal. And lastly, I used a GTM boundary from 2021 and a habitat system layer from the GTM Reserve Centralized Data Management Office, and you could see those in the previous map. As I mentioned, for this analysis, I'll be using NDVI, which stands for Normalized Difference Vegetation Index, and that is analysis that will be performed on that multispectral NAIP imagery I mentioned. And that is going to determine the vegetation health or greenness. And how it does that is using the various spectral bands from the multispectral imagery, specifically the near-infrared bands and the red bands. That is going to be the reflectance from near-infrared and the absorption of the red using the formula on the right there. And that's going to give me a range from -1 to 1 in values, -1 meaning no vegetation and 1 being healthy vegetation. Now, canopy height was derived from that LiDAR point cloud I mentioned, and to do that I used the LAS point statistics as rasters tool, which interpolates or creates a continuous surface out of those elevation points that were pre-classified, and that was used to generate a vegetation height raster. To pick out canopy height, that was part of the reclassification process, which I will go over next. The NDVI and canopy height layers were reclassified with the top 10% of each of those ranges of values. I used a 20 rate quantile in histogram on the right here for reference to kind of follow what I'm saying to find the 10% of each of those values and then assign them on a range from 0 to 2, 0 being not suitable, 1 suitable, and 2 very suitable. And you have to do that to be able to put it into the weighted sum tool, which is going to give me that suitability raster that I need. And in that tool, they will be given the same weight or the same importance for that. So the coastal forested areas within GTM that had both high NDVI and canopy height values were shown in that final suitability raster. So just the highest values from each layer. So this model did produce a raster that showed areas most likely to indicate archaeological sites, and from there I did simplify it down to just showing the areas that were the most suitable versus not suitable at all for the statistical analysis. When the final suitability raster was completed, I took the known archaeological site locations from my partner and I compared them to the results of the model to test the percentage of accurately predicted sites. From there, a one-tailed binomial test was conducted to determine if the percentage of the accurate predictions of site locations was statistically significantly greater than just performing a random sampling of the same amount of area. So to get into my results, starting with the NDVI analysis, which you can see on the map on the right, we ended up with a range of values from negative 0.98 to 0.63 as far as vegetation health. So when you're looking at that map, those green areas are going to be your upland forest areas, which are the healthiest or greenest, and the ones that are in red are going to be open water. The yellow values in the middle there are going to be more bare earth, which the amount of that is not incredibly surprising because most of this is a wetland. So there's going to be waterlogged plants or just dirt or sand. So the values that I reclassified, you can see the table I used there. Less than 0.296 were classified as not suitable, while values that were greater than 0.336 were given the high suitability for input into the weighted sum. Here on the right, we're looking at the vegetation height that was derived from that LiDAR. From there, we had values from 0 to 35.42 meters. I gave a little inset map there so you could really see the detail of the LiDAR and can make out the individual trees that were the highest in this location. And those are going to be those dark green values that are representing those. And as you can see, those are in the upland forested areas throughout the northern reserve. So heights less than 17.92 meters, they were classified as not suitable, while values greater than 20.14 meters, we were classified as the high suitability. And I did double check that by going back to the original points and making sure they didn't line up with anything that wasn't a tree. So after those were put into the suitability model, this is the resulting map that I had. It is kind of hard to see from this range, so I do have an inset for this as well to see the areas that I was marking in red. So this, like I said, is showing the locations of both the highest NDVI values and tree canopy height that's within GTM. You can see those in this imagery, which is the NAIP imagery, in those big forested areas going through mainly the middle of the park and those higher elevations. The areas marked as suitable actually only consist of 0.51% of the entire area of the northern boundary. So from this, my partner gave me the 62 documented archaeological sites that are found in the northern boundary. I did exclude underwater sites from this. So 31 or 50% of all of the sites contained areas marked as suitable by this model. On the right here, I can't give actual site locations, but you can see an example of a site boundary that did include suitable areas from my model. And from there, I used those inputs for the binomial test, which showed the probability of exactly or greater than 31 out of 62 sites being accurately identified in a other random sampling of an area of 0.5% of an entire area, was a p-value of less than 0.000001. That significant p-value does tell me that my model does accurately identify sites better than a random sampling would, and that it was able to accurately identify many of the archaeological sites using NDVI and canopy height as tree health indicators. And many of those sites that did have suitable areas within them were shell middens or rings, which further supports the background we talked about, that the shells do create a more calcareous soil, which changes the pH content and the drainage ability of the soil, which does help with tree productivity. Now the other sites that were not shell middens and rings, I cannot say without a soil analysis if they did have a high charcoal or wood ash content that contributed to this. That is an area of further study that would be interesting to pursue. And can it be used in other locations? It is possible, but it would have to be tested to be able to see that. With this and the study in British Columbia, it can be said that there's a lot of potential for it to be used in other coastal areas as well. Especially with the implications of sea level rise, this is where it is most needed at this time to try to rescue these sites before they are lost forever due to sea level rise. And another part of that is it could have affected the model. So some of these sites that may have been pinged as being suitable in my model may not be because of sea level rise. So when the water is coming in and there's a lot of inundation, the tree health may decline. So trees that may have been healthy and may have shown up on the model might not be because of sea level rise effects. You can use older imagery to try to combat this, but at the same time, it is a bit of a crunch on the timeline to try to find these sites and save them. So to conclude, using NIIP multispectral imagery and LiDAR point cloud data in this case to find NDVI values, using vegetation indices and canopy height values to show tree health does significantly accurately predict site locations in this area as opposed to random sampling. So when paired with these, they do serve as a good indication in a mixed canopy forest where crop soil marks could only work previously in a more homogeneous growth. And another very positive thing is this method is very efficient and cost effective, and it can be used quickly to find these sites when you have a big storm coming in, or just the effects of sea level rise are catching up with you. So there's a lot of room for future research here. Like I mentioned, doing more of a soil composition analysis at these sites will give some more insights, and going and doing some ground truthing to test to see if there are sites in other areas that the model indicated that did not already have known site locations. And also looking at the tree type would be an interesting avenue to pursue. And this opens up a lot more research into using remote sensing for these purposes and learning more about how archaeological site composition can be affecting vegetation. So with that, thank you for listening to my presentation, and here are my references.